Well, thanks for coming out, everybody. I'm Dr. Goodman, and had the pleasure of working with Nick Schneider and Mike Perry. They're going to talk about a self-balancing robot that they worked on this semester.
Good afternoon, ladies and gentlemen. My name is Mike Perry. This is my partner, Nick Schneider. Over the course of this semester, we chose to do a senior project over a self-balancing robot. Over the contents of this report, we plan to cover the project inspiration and objective, as well as project requirements, some background information pertaining to the project, a code and design overview, our current progress on our project, a component selection as well as an economic analysis. Finally, we plan to cover the project challenges, any future endeavors, our learning experiences over the course of the project, and a conclusion. That's much better. Okay, so at the beginning of this semester, Nick came to me and said, hey, I've got this idea for a senior design project. This is what I want to do. And basically, he showed me a clip similar to this. And in this clip, we have a self-balancing robot. We have a two-wheeled robot that stands vertically and is able to move back and forth across the floor. This is what we were going to attempt to do. So for our inspiration and objective, the inspiration from this project, or for this project, came from a clip similar to what I just showed you. The core objective for this project is basically how to use a robotic design to balance an unstable inverted pendulum. Because we personally funded the project, we were allowed to pick the requirements ourselves. So for our project requirements, to be a success, our robot had to be designed and fabricated. We had to design and implement control. We had to make the robot capable of righting itself and maintaining its balance. And we had to feature a Raspberry Pi MATLAB control combination. So whenever I say balance an unstable inverted pendulum, what exactly am I talking about? Basically, what we have here is a side view of our finished robot. You can see that we have an axis about which the robot will attempt to rotate here, and we have a top-heavy structure. Basically, we have a lot more above the axis than what we have below the axis. The end result of this is that we have an unstable system that if it's not powered or propped, it wants to fall over. Now looking at this image here, you can compare it to this schematic. And in this schematic, we have a few certain variables or parameters that we're going to be paying attention to. We have our linear displacement here, our angular displacement here, which will correspond to this value phi. We have our linear displacement here, which will correspond to this position x that the robot will have to move to stay balanced. We have the axis of rotation here, which corresponds to this point, as well as a center of mass located here, which on our robot is somewhere around here. So after you've seen all of the values that we need to monitor, these values correspond to states within a model that we'll show you later. This model, in order for it to work, has to know the values for our angular displacement, angular velocity, which we'll call phi dot, our linear displacement x, as well as our linear velocity, or x dot. These values are collected by sensors which then they are sent to a microcontroller. This microcontroller performs balance adjustments and sends them to a motor driver. The motor driver amplifies the signal, which then is sent to the motors, which turns the wheels, and the system repeats. So a very simple code overview of what's happening internally on the Raspberry Pi, or I should say in the MATLAB code. Basically, we initialize our code. We then gather all of our sensor values. The code calculates our balance adjustments and then powers our motors in order for the system to adjust. And at that point, it loops back around and gathers the values again. The first task that we had to complete before we could actually begin control design was we had to derive a model for our unstable system. In order to do this, we had to take several measurements. We had to perform mass measurements, length measurements. We had to perform center of gravity calculations as well as mass moment of inertia calculations. We also had to perform calculations to obtain our motor constants, as well as we had to measure the resistances of our motors. Finally, after doing all this, we were able to model our system.
All right, this is our state space model. It looks pretty scary, but it's not too bad. Basically what we do is we use the parameters that we just found in the last slide and plug them into this model. This allows us to understand how this system is going to respond and allows us to start control design. Okay, so like he said before, we needed our angular displacement, and that is the tilt angle from the desired position here. We also need the angular velocity, which is the tilt speed, and we also need the linear displacement or position x, which is where we want it to be, and our linear velocity, which is how fast it gets there. So we only have two sensors. We have the gyroscope here, which measures phi dot, or the angular velocity, and we have the accelerometer, which measures the acceleration in the linear direction. But as you can see, we can only measure directly phi dot. So how do we attain the other state variables? There's two options we could take. We looked at an observer estimator. This basically takes those sensor values and estimates the rest of the states. One such estimator is a Kalman filter. We also looked into full state feedback. For this to happen, we need to measure all the values directly. So we can do this through integration. The integral of phi dot, or your angular velocity, is the angular displacement. The integral of the acceleration in the linear axis gives us the linear velocity, and the double integral of our acceleration gives us our linear position. We also looked into sensor fusion techniques such as the complementary filter. What this does is take two sensors and combine them together in order to get a better accurate reading. But the gyro tends to drift from the actual value or lag, and the accelerometer is very noisy. So what we do is we do some trig to obtain the angle from the accelerometer, and we take the integral of the gyro value, which gives us our angles. And we put those into the filter, and as you can see, the angle that the accelerometer gives us is very noisy. And the gyro angle is good, but it lags from the actual value. So putting it in the complementary filter, which is the red line here, gives us a more accurate value. So we're going to talk a little bit about sampling. because the microcontroller is a digital device, and therefore we have to implement our control in discrete time. So what is discrete time? Well, this is a continuous time signal, which is kind of how I'm talking to you. You're registering all the values available. But through sampling, we have to take values from different points along that line, which corresponds to a time value, which gives us this signal here, and if we filter it, we can approximate the actual continuous time signal. So our sampling rate is 33 hertz, and our sampling time, which is 30 milliseconds. What this means, the 30 milliseconds is the time between each value we obtain from the sensors. This limits our system to a 16 hertz bandwidth, which we simulated a stable system in MATLAB, and we believe this approach will work. But the reason why it's a little bit slower than what we'd like is because of how MATLAB works when it's programming the Raspberry Pi. So MATLAB runs inherently onto a computer. It sends the code to the Raspberry Pi, which then asks for sensor values. The sensors then go back to the Raspberry Pi and back to MATLAB, which makes it a little bit slower instead of just making it run back and forth between Raspberry Pi and the sensors. So we looked into increasing the sampling rate. There's a couple ways we could do this. We could use Simulink, which downloads the code, and then it just runs on the Raspberry Pi back and forth between the Raspberry Pi and the sensors, which would decrease our time. But Simulink lacked an inter-integrated circuit, or I2C communication block for the Raspberry Pi. Basically, we would have to create our own, and that would take time. So we couldn't go that route. We also considered using Python or C programming to also make it run inherently on the Raspberry Pi. But we have to rewrite our entire code, which would take even more time. So we decided to go that approach with full state feedback, but we came up with some errors due to discrete intervals. As you can see, we get a linear velocity that seems reasonable, but when we double integrate the acceleration, we get a very small value close to 0, even though we're moving it over an inch. This is the value that we obtained, which is 0.015 meters, which if it were an inch, it would actually be 0.025 meters. So we had some error there. We also had the gyroscope stop working about a week ago. So we had to come up with a new way. So we decided to use an estimator, and we're in the design process of designing a Kalman filter to estimate our states. So our current progress. The robot has been designed and fabricated. The system has been modeled. The sensors are functioning, and components are communicating properly besides the gyro. Motors are functioning. When we send it signals, the wheels turn. But the balancing control has been written, but we're in the tuning phase. So this is our Raspberry Pi, which is our microcontroller we use. It's compatible with MATLAB. It's capable of I2C communication. It offers a pretty fast processor, and it came to us at no additional cost because we already owned one. Here's our sensor package. It actually contains 3 sensors, an accelerometer, a magnetometer, and a gyroscope. We decided, for this project, we will only be using the accelerometer and the gyroscope, and it's also capable of I2C communication.
So after we had settled on a suitable microcontroller and a sensor package, we had to select power sources that would work with the microcontroller. And we chose to go with a 2-battery power source system featuring a Tenergy lithium-ion plus battery, as well as a portable battery charger. Basically, the reason we chose to go with 2 batteries rather than 1 is because using a second battery allowed us to isolate the microcontroller from the motor power source, the end result reducing our sensor noise. After selecting our power sources, we then moved on to select our motors. We chose to go with Polu 34 to 1 metal gear motors. These feature integrated encoders that can be used to obtain more precise control, and they require 12-volt power source with a 2.1 amp stall current and a 200 milliamp free run current. So they were compatible with the power sources that we had chosen. Since we had motors, we needed a motor driver. We chose to go with the Devantech MD25 motor driver, which was compatible with our Polu 34 to 1 gear motors. It required a 9 to 14 volt power source, so it fit our power source requirements. And it was capable of communicating over I2C. Once we had purchased our motor driver and tried to hook it up to the microcontroller, we found a problem. Basically, our motor driver wanted to communicate over I2C between 0 and 5 volts, whereas Raspberry Pi is only capable of communicating between 0 and 3.3 volts. Incorporating this motor driver incorporating this level shifter allows the motor driver to speak to the Raspberry Pi without causing the Raspberry Pi damage. Once all of our electronic components were selected, we then designed the frame. We chose to go with a 2-shelf aluminum 6061 frame. It offered sufficient space for all of our components that needed to be mounted. It was constructed of a lightweight material, and the way that it was designed would allow for quick disassembly in case any modifications were needed. The last component that we're going to mention is the Polu 70 millimeter by 8 millimeter wheels. These easily adapt to the gear motors that we chose to use. They placed the robot at a sufficient height that allowed for balancing, but the height that it placed the robot at was low enough that if the code was shut off, the robot's frame could actually act as a prop and keep the robot from falling completely over. A quick economic analysis of all of our components. You can see here the main components I'd like to mention are the Raspberry Pi microcontroller, which cost us about $39.95. The 2 Polu gear motors cost a total of $69.90. Each one was about $35 a piece. And the Devantech motor driver cost $51.61. In total, our component cost for the project was about $250. So there were challenges that we ran into over the course of this project, just like any other project. Significant research had to be done in order for us to even attempt state space control design. Achieving a stable system so that control could be implemented gave us some trouble. And researching how to obtain our unknown states took a lot of time. Until this project, I've never researched a Coleman or a complementary filter. Some future endeavors for the project. We'd like to incorporate the encoders to further stabilize our system. We'd also like to implement a control design that would allow the robot to move forward and backward, as well as heading control that would allow the robot to turn. Finally, we'd like to incorporate a mapping function within the code that would allow the robot to be forcibly moved from one position to another, and whenever that force was removed, the robot returned to its original position. Learning experiences over the course of this project, we had to learn how to do state space control. We definitely learned the importance of a stable, discrete time system whenever applied to control design. Time management techniques were a big factor over the course of this project. and the value of careful planning whenever it comes to selecting your electronic components. There was more than one time that we had to cancel an order because we overlooked a certain spec. So to conclude, our robot currently does not balance, but we did meet 3 of our 4 requirements. The robot has been designed and fabricated. Control design has been performed and implemented. The robot does feature a Raspberry Pi to MATLAB control combination. Regarding the robot's ability to balance, we're currently in the tuning phase. We'd like to acknowledge Dr. Kevin Goodman, Dr. Ronald Deersing, as well as Justin Amos at the AEC, and finally Donna Moore for chasing us all over the engineering building and making us turn stuff in. Are there any questions?
There's another microphone.
Which one?
Just take it down.
With regard to your integrations, are those all performed in 3 dimensions?
No, they are only performed in 1.
Nice job, guys. I was wondering if you considered, because you had some issues with the speed of the processing power, that's what I was gathering, if you had thought about maybe changing the center of gravity to make the robot itself a little less responsive in order to match that processing speed.
We messed around with it in the MATLAB code and, raising it and lowering it, just seeing what happens. But we never got around to actually moving it. The biggest problem we had with that was we'd have to drill again and everything, and we looked at that too late in the project.
When you use MATLAB to download to the Raspberry Pi, is it autonomous then? Does the Raspberry Pi hold the controls?
No. All of the computations and stuff, all of that is done in the MATLAB code. That's actually probably one of the main reasons that the system itself is delayed, because the Raspberry Pi in this configuration actually acts more as a slave than a master. Basically, MATLAB does everything. The microcontroller just forwards the sensor values to MATLAB and records the control request from MATLAB out to the motor driver.
Do you see an easy transition to making it autonomous from just downloading it onto the Raspberry Pi then, once you have your debugging completed?
Can you repeat that?
So right now you're really using MATLAB as a debugger, right? So how do you see going from this debugging state and getting the system running to making it autonomous?
We believe we could use MATLAB as it is. It's just going to take us some time to tune it. But it would probably be better if we, and I do plan on continuing this, if I just go ahead and program it in Python.
All right. Any other questions? Let's give them a hand. All right, folks.